There is a growing tendency to use technology when taking care of the plants. Also, in the terms of investigation from transgenic and hybrid seeds. As they are being kept and growing in a greenhouse, there is also a need for developing technology to use in such kind of greenhouses. An example of this technology is the irrigation system the greenhouse uses to take care of the plants. It must save water, but at the same time, the plants must not lack of it. So, why not adding technology to the irrigation system and giving it a plus respect to other greenhouses or systems applied to them? For this, the think thought about controlling the amount of supplying water by this kind of system in order to keep on with the water saving idea. To achieve this, it is necessary to control the water flow through the system. So our goal is to design and construct a system capable to control the water flow in the irrigation system for a greenhouse in a level established by the user. Our functional blocks. HMI. The function of this interface is to display the system behavior and change the reference according to the needs of the user. This interface was made in LabVIEW. Arduino. This is the data acquisition system. Water pump. Its function is to provide the water needed to maintain the level in the tank. Sensor. Measure the water level in the tank. In this graph, we take the value of the potentiometer attached to the flutter. This is our water level sensor. The values was measured with LabVIEW and exported to Excel. Then was copied to MATLAB where were plotted. And the reading of the sensor is our open loop values. And then we approximate the transfer function to the system seen in class, which is a control level system. This system is h of s is equal to k over tau over s multiplied by s plus 1 over tau. We tested different values of k and tau to get a transfer function which approximates to our plant response. And according to the graph, we get h of s is equal to 0.03 over s multiplied by s plus 2. Now for the compensator, we need to check where are the poles of our plant. For the transfer function, h of s equal 0.03 over s multiplied by s plus 2, we can see that we have a pole in the origin and one pole in minus 2. So we decide to use a PID compensator, which gives us 2 zeros and 1 pole in the origin. And we can cancel out 1 0 with the pole in minus 2. Now we need to define the values of Ts and the damping constant. Our Ts is equal to 300 seconds and a damping constant equal to 1 over root square of 2, which gives us a value of sigma equal to 0.0133 and WD equal to the same value. Now we force the root locus to include the ideal position of the poles. This is with the arrival angle. The formula is minus the summatory of all the zeros plus the summatory of all the poles plus 180 degrees, which gives us an angle of 90 degrees. This tells us that our zero is just below in the desired position of the poles. So the root locus must look like this. And now we can calculate the values of Kp, Ti, and Td and put it in the program. So we need to multiply our compensator with our plant and evaluate it in minus omega d and sigma. This evaluation gives us a value of Ka equal to 88.9. And now we can calculate the value of Td and Ti. The Td is equal to 1 over C1 plus C2, which gives us a value of 0.497. And the Td is equal to 1 over C1 multiplied by C2 and multiplied by Td, which gives us a value of 75.5. And finally, the value for Kp is equal to Ki over Td, which gives us a value of 1.79. With this value of the compensator and multiplied by our plant, we have a closed loop system response like this, which is stabilized in 5 and have an overshoot approximately of 75.
Okay, now I'm gonna explain you the block diagram we designed to the PID compensator in LabVIEW. In this first section we have the initialization of the communication with the Arduino. Then this block is a configuration inputs and outputs for the Arduino, and then the first thing we do is read the signal of the sensor, of the level sensor, and this signal we rearrange the data of the signal to the 0 to 100 to show it in the tank level, that is this, and in the chart. Also we have the reference, that is a slider, and the data of this slider we rearranged from 0 to 100 to 0.21 to 5.0127. To get the error of the system, we subtract to the reference the real value read by the Arduino, and then divide it by the reference value and multiply it by 100 to get the error in percentage. We also plot in the chart the reference point to see the two graphs, the reference graph and the real value of the reference. Here we can see the reference value is in red with a change from 5 to 10, and the real value is changing from 5 to 10, but in this way. With the error percentage, we multiply it by Kp to obtain the proportional part of the PID. To the integral part and derivative part, we get these two arrays. That is the history of all the errors. In this array we have the actual error, and in this array we have the last error. For the integral part, we added these two errors and divided by 2 to get a mean value between these errors, and then we multiply it by the sampling time and added this value to the last value, and the result we multiply it by the division of Kp over Ti. Then we multiply it by a on-off control. For the derivative part, we subtract from the actual error the last error to see the change, then divide it by the sampling time and multiply it by Kp and Td, and also multiply it by the on-off control. All these values was added to get the control for the for the pump. In this part, we check first is if the value of errors are less than 0. If it's true, we send a value of 0 to the pump, and also we ensure that the pump stopped. Also, we have a emergency button to stop the pump, and when we stop the cycle, also the pump stopped. When we have an error greater than 0, then this error was rearranged in a range of the values for 0 to 255 to send it to the pump. In this block, we activate the pump with the mother shield, and we also plot the the values of PWM we sent, and we also have a indicator of the PWM we are sending. In this graph, we can see the values of PWM we are sending, and in this indicator we see the value. Now we can see the interior of this VI. It's so simple, only is 2 digital grids and 1 analog grid. With the digital grids, we say to the motor shield the direction and if we need to stop or not the pump. And with the analog grid, we say the amount of PWM we want to send to the to the pump. When we decide to end the cycle or an error occurs, the cycle stops, then we close the communication with Arduino and show the error if is the case. The closed loop, the while loop, is controlled by a sampling time that we decide with this slider that is in seconds. We multiply the value of the slider by 1000 to get to this block the time in milliseconds.